Good morning. My name is Dominik Michel, head of the consulting and projects team here at Mass2Market. During my time as an application engineer, I had the opportunity to realize a couple of service projects for our different business areas, increasing productivity by automating tasks with GeoPy. So I'm pleased to show you some of the concepts and examples today. And as I've seen on the agenda, I have a bit of time, so let's start. Okay, so increasing productivity, automating tasks with GeoPy. What is the goal here? We all use Geodict, but we want to use it better. We want to automate tasks, we want to have reproducibility, collaborate with colleagues, increase productivity, and in the end, using GeoPy to using Geodict better. The Geodict functionalities, thank you very much. Geodict functionalities to enter this world, macros, and actually your workflows, what you're doing there. So the first step, record and play back your workflow. While you do your workflow, Geodict is actually already and automatically recording it in the background. There's the session macro, which is seamlessly integrated and prominently visible in the Geodict UI. Here, for example, while we're generating some structure, adding binder afterwards, running a flow simulation, all while we're doing that in Geodict, it's actually already stored in the background. So here, for example, on the right-hand side, you have seen the session macro window, as I mentioned, seamlessly integrated, prominently visible. There you can easily store your commands or copy to a scripting environment if you desire. But the first feature is here, of course, that we can have a simple playback to rewind and reproduce. Here, for example, as we seeing it here, setting the material parameters, setting up the flow simulation. And while this is running, again, on the right-hand side, actually the session macro is visible. We can copy that to our macro, store it there. We have already stored what we have done. We have recorded it, and that without the first steps into the scripting world, without doing any scripting yet. We are just storing the macro and having the script of what you have done. You have already documented that. So the first thing here in terms of automation is, well, actually documenting your workflow can be easily done in Geodict. And here, as it's stated here, it will rerun the same parameters, the same commands, and you get exactly the same results out of that. So, but I think we don't need to follow this video until the end, isn't it? Well, maybe a second. So, okay. So after that, as I mentioned, you have done the first steps into the scripting world by documenting what you have done. The next step is then, of course, to increase your productivity, and that's then where it comes in the automation with GeoPy. I just skip on that. So, can you shrink that? So the automation in Geodict is possible through the use of GeoPy, a Python extension in Geodict. Well, we're aware of the peak demands in the core analysis labs. So we offer the full automation and cloud computing to reach a level of scalability that is suitable for reaching your project goals ahead of time. With our Python interface, GeoPy, as already mentioned, you can easily automate repetitive tasks, perform parameter studies, generate comprehensive PowerPoint reports. With access to the entire range of the Python coding, you can automate just about everything in Geodict. With all the available functionality of the Python universe, such as modules like SciPy, NumPy, for example, you have the full flexibility of scripting language at hand. And with all the workflows set up, the cloud computing with Geodict might be a path to consider. And we do actually offer cloud options such as software as a service solutions. But automation with Geodict goes even further. We have created Geo apps to eliminate the requirement to write Python for the workflow user and to integrate your automation seamlessly into Geodict. So GeoApps, create customized workflows tailored to your needs with GeoApps. They extend and customize Geodict to automate and simplify complex workflows, seamlessly integrate and centrally control various functionalities within Geodict and its modules. They are powerful tools to automate, simplify, and extend Geodict's range of capabilities with a user-friendly interface adapted to the Geodict UI, as well as standardized result files, as we have already seen a bit of that in the previous talk. Creating your own GeoApps, you can efficiently manage development workflows according to your needs. As I mentioned, automating workflows, simplifying complex workflows with user-friendly UI, just reducing the number of parameters to those you actually want, but actually doing the same module, the same run, and the same tasks you actually wanted to do. And additionally, as I mentioned earlier, with the Python modules available, you can add individual functionality to the workflow through GeoPy and the complete Python universe, SciPy, optimization routines, NumPy example. And of course, you can share those GeoApps with work colleagues or the scientific community, simply creating GeoApp through GeoPy. Now that a bit on that. Now in the following, we'll have a look at some of these, which are available with Geodict and coming shipped with the Geodict releases. So let's first start with an example we already had on the screen, but I want to have a different angle on that. That would be the generation of digital twins of nonwoven require a lot of manual work, as we have seen yesterday, to match the original geometry, especially curvature, curliness, required a lot of trial and error there. We'll see on the next slide, the current FiberFind and FiberGeo versions allow a direct comparison of the geometric properties. So the non-woven digital twin app takes FiberFind results and implements an automatic optimization loop to find parameters not directly computed by FiberFind. What you can see here on the screen is actually the seamless integration of these GeoApps inside Geodict. In the middle window, that's the location of the GeoApp within the Geodict UI. You can see that there's the classical parameter edit window with a small parameter list, which is actually necessary for this GeoApp. Everything else is computed internally. Then a small description actually highlighting what this script is doing. As I mentioned earlier, with the GeoApps you can create yourself, then this would be the place where you can tell your colleagues, can tell those who use this GeoApp to actually what is this actually doing. The line open macro and script files actually the access to see what is done inside, to have inspiration on the handling of variables of the UI elements. For example, on the right-hand side, the UI with some label information, some variable handling, and so on. And then, of course, the classical run in the cloud and run in the job queue buttons. But coming back to the GeoApp itself, let me see. There is some double in there. In Geodict, so in Geodict 2023, we have seen the slide already. We're making this parameter comparison easier when creating a fiber structure with FiberGeo. It displays the same statistics that could previously obtained by FiberFind. So having the same parameters also enables optimization schemes. But this is why what I mentioned with hiding actually complex workflows behind a very simple UI, that you can actually, here there is an optimization loop, optimization routine in the background. You don't need to handle that. You don't need to parameterize that. It just does its stuff. And then you get a nice digital twin out of that. And what we've seen yesterday already, or in the previous talk, I think, was then the result here to generate a fully automatic, only from FiberFind and Mantic GDRs within a few hours, compared to a lot of time to manually tune that, comparing the original on the left to the digital twin on the right-hand side. As we have seen already, this is a statistical digital twin, so it doesn't need to be visually visually identical, but the geometric properties or the properties you want to have to where you have compared that are identical here. Okay. Another geo app coming also in the area of structure generation is the generation of artificial microcity scans. It's based on geometry model available in the new GEDIC version. This GEAP can be used to create nice visualizations of geometry models, make them look more realistic. But there are also more applications which we will see in a minute. Here also, for example, the UI in the middle, as you can see, same design, same structure, bit of different description, of course. The parameter window also completely generated in our scripting language in Python using our GeoPy interface. In this case, we have a table to enter the parameters, some drop-down menus, a bit lengthier than that, but still having an overview on that. Creating artificial micro-CT scans, especially adding here some noise and image artifacts. You can see the list on the right-hand side. And can be used for visualization, testing, validating data, so image filters and training neural networks, for example. So to train AI labeling, for example. Here in this case, this is actually quite fast. In this case, we don't have any ray tracing or beam simulation. The task here was to have very quickly, very efficiently micro-CT images from a structure, creating a micro-CT scan in just a couple of minutes allows you to have a lot of data with different artifacts, different different filters, and to have a lot of training data for an AI algorithm on that. Why is this one here not too? Here, for example, would be to have the optimal setting for an image import process. I can also show you some comparison between an original CT scan, then we have the segmented data on that, and creating out of this one an artificial micro-CT scan again, and you can compare the left and the right-hand side. See that's what the difference is there, and maybe we can also then tune the segmentation to actually better fit the original micro-CT scan, which is another workflow using this Geo app internally. It's actually possible too. A macro of a Geo app can actually call another Geo app. It's just your workflow done in a scripting language. Okay. Another one on terms of the structure generation part would be the generation of a granular statistical digital twin. Similar here to the first one is that the generation of a digital twin of a granular structure always requires a lot of manual work to actually fit what you are looking for. Here in this case, choosing an optimization workflow can automate that, but requires actually programming and mathematical knowledge. This Geo app removes this requirement and offers a usable front end to a complex matter. You can see the complex matter here because actually the parameter list is quite more extensive than in the first example. But here also, this parameter list is completely written in our Python interface. So here, for example, again, seamlessly integrated, the same design as GEDIC UIs. And what we're actually doing here is, task here was to combine the structure generation with the stochastic field thresholding with Gaussian random fields. So there was a cycle to at first recreate the modeling of a standard reservoir rock. So actually be applied to any grain-based structure. We have the classification of physical parameters of the reference sample, which is indispensable for sufficiently accurate modeling of a digital twin. This high level of information can be accessed by calculating, for example, not only pore size distribution, but also grain size distribution, chord length distribution. That's what actually made the UI more larger, because one could choose which parameters to optimize on, which parameters are those which are interesting, which should be fit here. In our approach here, the reference ROC is then modeled by approximating user-defined parameters. Again, one can change the user-defined parameters, so even here, some more functionalities here. And then the functional parameters necessary for modeling can be changed, as well as the error measures. And those are set as stopping criteria for the optimization loop. And after the optimization loop, you can see on the lower one, we can generate a statistical digital twin, which is then compared to the reference values. And this will chosen to change the generation parameters to get the next structure in the next iteration in the next loop. Down there, for example, on the lower left, you can see the reference and the approximation, and the pore size distribution and the grain size distribution were used as target values. You can see both are nearly fit quite well. What we've introduced, this was actually from in GEDIC 2023. With in GEDIC 2024, we improved this GeoApp to create a 3D digital twin based only on a 2D image. Well, as we've heard yesterday, in general, as 2D images are much easier to acquire and much cheaper. For example, here is a 2D SEM image of a solid oxide fuel cell cathode, where the original image is shown on the left, and the created digital twin is shown on the right. In this case here, the 3D structure, just one slice, will be used for comparison. As we get the information from the reference on our 2D slice, we can compare those results to fuel our optimization algorithm in the background. As you can see in the total error in the table, there's not much difference compared on this single slice on the reference values on this single slice. Okay. As I mentioned here, an example with a solid oxide cathode in this case, maybe also highlight you one GeoApp hiding another complex structure generation algorithm, the GeoApp for the solid oxide electrode generation. As you can again see here in the middle, the seamless integration, and on the right-hand side, our UI, this time also with integrating material phases. Here we're targeting the electrochemical conversion device, which produces electricity directly from oxidizing a fuel. Of course, we have the flexibility to use different fuels, but for the solid parts, the fuel operates at very high temperatures, so we require special materials to be set and used, which also had an increase in the material database last year as a consequence on that. So this app here called the solid oxide electrode generation. This was originally presented by Philippe Mamet from the Institute of Computational Physics of the Zurich University of Applied Science, actually at the GEDIC user meeting 2 years ago, 2021. That's the structure generation is based on Gaussian random fields with a field variable that takes random values and thresholds them with a correlation function to truncate Gaussian distributions to actually get a virtual three-phase structure with a standard deviation of these Gaussian fields to be chosen for the typical pore and particle sizes of the microstructure. Purpose on this here is if you can generate these solid oxide electrodes fast and easy. At first, of course, we were hiding a complex geometry modeling, in this case non-granular, non-fibrous, easily generated, realistic ceramic structures behind a GeoApp. You don't actually need to see what the details are in there. It's just you use that GeoApp and you get a structure with this purpose. And on this times here, the fast and easy construction of a stochastic geometric modeling and associated realization of digital twin, as here as an example, is the material design for the solid oxide fuel cells. The microstructure characterization and effective and relative transport properties can be done on a large sampling database. As soon as you get real data, you can compare that with your database and already pick the best suited digital twin. It's already generated in this database. But these were now several GeoApps for structure generation. Of course, other workflows too. So here, for example, one GeoApp that simulates the process of aging of rock samples. We have different approaches there. Again, in the middle on the right, you can see the UI and the parameter window. We've already heard a bit about that yesterday. I will show you a bit about that. But here again, the GeoApp combines a simple front end, various complex workflows in the background, because there are actually 3 aging methods implemented behind that, and a standardized output. As we have earlier in the previous talk, the result files, we can generate them with GeoApps too. In this case, we have a standardized result file, very simple input parameters, just stating here, okay, I have a water phase, an oil phase, and I want to simulate the aging of my rock. Different approaches. I'll come back to that in a second. I think I have to speed up a bit. So the purpose here would be to simulate a 2-phase flow with GeoDict. You can compute drainage and imbibition, and hysteresis cycles, change in fluid content. But actually the context angles on the solid boundaries are changing. Simulating rock aging to incorporate the wetting behavior is crucial here. The option to differentiate between 3 different approaches to change these context angles is actually the task of this GeoApp. The illustration here shows spontaneous imbibition here in the water left part, or the mixed wet Gilderheiser sandstone, and you can see on the right-hand side that the consideration of wettability changes is actually crucial to fit the experimental data on there. So the wettability changes are essential here. Now, how would be the digital aging be done? What I mentioned is behind this GeoApp, there are actually 3 different approaches. It can just be a simple one, reassigning all non-wetting phase contacts with the rock to become actually non-wetting. The stochastic approach would then be, if you just don't want to have this single case, the current state, say, okay, it shall be a randomly distributed wettability change up to a certain degree. And of course, we have the deterministic approach to actually change the wettability with respect to the pore throat size and non-wetting phase distribution. Okay, so much for a lot of the GeoApps we have currently in GeoDict. I just have small sneak peeks left on my list, and I see the timing, so that should be a bit faster. So one would be the GeoApp called reverse engineering, but it's not reverse engineering everything. The point here is if you have a multi-component composite, and you have a given strain stress data for that, but you have missing mechanical properties for one material, then you can fitting those parameters to actually fit this unknown mechanical property so that the measurement results you have are actually hit better. So then here also in this GeoApp, this script actually, it's not yet a GeoApp, it's a script at the moment, can include different material laws, different damaging rules. Exactly. And last but not least, a small sneak peek that we're also working on the water condensation in gas diffusion layers under humid and warm condition that you actually have the fluid included, well, condensating on a structure. So summarizing on that, we wanted to use geotic better. What we've seen today is easily editable workflows, reproducibility at the beginning, that you can store and rewind your workflow, that you can use GeoPy to tailor your workflow to your needs. They have huge simplification on that the UI only covers those parameters you actually want to use and not everything which you won't change. And then you have removed the human error component and actually doing, for example, the parameter study was just one value. All the other parameters stay the same, so you can enforce it to be staying the same. With that, I mentioned parameter study. You also have the automation, and as a GeoApp distributable, you can share it with your colleagues and with us too. So summarizing on again here, at the end, an easy-to-use scripting language, additional libraries come ship with Geodict. You can use the Geodict API, the functions, the usability tools, making result files with plots on your parameter studies. At the end, increasing your productivity with automating tasks at your fingertips. And major highlight on that, it's all in an all-in-one solution and fully integrated into Geodict. So at the end, let's write your own GeoApp or let us do it for you. Thank you very much for your attention.